Hello again. In one of the previous tutorials, we have talked about optical constants and wave propagation within materials concerning the speed of light and the absorption of radiation. This tutorial is about interfaces between two different materials. So we will first talk about light waves at interfaces, just single interfaces between two materials, and then we will take a look at wave propagation with many interfaces and layered structures or in three-dimensional theories. In particular, we will cover the topic of thin film optics, where you have very thin layers with thicknesses in the range of the light wavelengths or smaller, which shows some very special effects that can be used for enhancing the properties of all kinds of products. Okay, let's take a look at light waves at a single interface. And here is a little animation that shows a light wave approaching from the left side in vacuum. Here is an interface between vacuum and the material to the right. And what we can change here is the optical constants of this material, N and K. N was the real part determining the speed of light. K is the imaginary part, and that tells us about the absorption. What we see here as a number at the bottom is the intensity reflectance. That means the intensity of the reflected wave in percent, not in percent, scaled between 0 and 1. So this number 0.47 would mean 47%. So let's take a look at different values of N and K, like we have done in the discussion of optical constants. Let's first look at dielectric materials where K is 0. And let's start with N equal 1 or almost equal 1. In this case, the material looks like vacuum, at least for the light waves approaching from the left side. And in fact, there is no interface at all. The light waves come from vacuum. It sees something like vacuum with the same optical constants. And for light waves, that means there is no reflection. Everything is transmitted. So there's nothing going back except the tiny little wave here, which is due to the fact that I didn't pick 1.00 exactly. But the intensity reflectance is very small, it's 0. And this changes, of course, if we make the material different from vacuum. Let's say we go to 1.5, a typical value for glass and the visible. Now there is a significant wave going back. The intensity reflectance is 4%, and that's a very typical number for an interface air glass. Almost for any wavelengths, it's about 4%. We have seen that the refractive index shows normal dispersion. That means in the blue, the refractive index is slightly higher than compared to the red. So that would mean if we go to a higher value, the intensity reflectance is also a little bit higher. But for glass, this difference is really very small. If we go to materials like tin oxide or silicon nitride with refractive index values of something like 2, the intensity reflectance rises to 11%. Let's take a look at a diamond interface, 2.4, indivisible. Then we have 17% reflectance. And finally, we can take a look at materials which have a very large refractive index, like silicon, 3.4. Reflectance is about 30%, or germanium, N equals 4, roughly, with 37% reflectance. Here again, you see that the wave that penetrates into the material uh, is slowing down. So due to the smaller wavelengths, but the same frequency at the interface, the wave propagation here is much slower. The speed of light is smaller in germanium compared to vacuum. It's only about 25%. Let's introduce a little bit of absorption. Basically, if you have weak absorption, it just brings down the amplitude of the light wave within the material. This has usually not too much consequence for the reflectance at this interface here, as long as K is small. If K is in the same order of magnitude as N, let's go to a typical metal. We have discussed that, like chromium or titanium. Then K contributes also to the reflectance. So now the reflectance is 34%. Without K, it would be only 9%. It would be smaller. So K takes influence on the reflectivity. And if we go to a noble metal with large value of K and small value of N, you can see that the reflectance gets really high, 87%. This would be something typical for aluminum. If we go to extreme values like silver, then we can achieve reflectance coefficients of 95% or more. It looks like the complete wave is reflected, but please note there is some light penetrating into this noble metal, which is absorbed in a very thin surface area. This is called the skin effect, and this absorption can be pretty dramatic if you use this material as a mirror, and if you have a strong light source like a high power laser, then maybe 5% of absorption in a very shallow layer of a few nanometers only can lead to a melting of the mirror and a real damage. So that already tells us now metallic mirrors are not really a very useful tool for high power laser mirrors. There we need something different. We will discuss that later on. Okay, that was a light wave approaching a single interface. Let's take a look at different angles of incidence. Actually, we just took a look at 0-degree perpendicular angle of incidence of light up to now. If you go from 0 to 90 degrees, very oblique incidence of light. What I show you here are two curves, the amplitude reflection coefficient, that means the amplitude of the reflected wave as a ratio to the incoming amplitude. And there are two curves, a red curve and a blue curve, which are really completely different. And these belong to two different situations called S-polarization and p-polarization. I will explain that in a moment, what that is. And but before I do, we can take a look at the intensity reflection coefficient. That's basically the square of this amplitude reflection coefficient, and also the square, the intensity reflectance, is very different for the S-polarized situation and the p-polarization. Actually, in p-polarization, something really dramatic happens here. There is a certain angle where the intensity reflection is 0. There is no light reflected at all, although there is an interface between, let's say, air and a solid material with a high refractive index. In this case, it's 2.4, something like a diamond. And what you see here is the 0 in reflectance that can be used for some optical elements between it filters out a certain polarization. This special angle here, where the intensity reflectance gets 0, is called Brewster angle, and it's directly related to the refractive index of the material that we are looking at. So if I change the refractive index, let's say to 1.5, typical for glass, you can see that the Brewster angle gets smaller values, something like 55, 56 degrees. It's hard to tell because the curve here is really very flat. There's a large area of angles where the p-polarized radiation is not reflected at all. And this angle, the Brewster angle, shifts with the refractive index. If I go to higher values, the angle gets higher. And so does basically the average reflectance of both polarizations added. So what is S polarization and P polarization? I have prepared a sketch. Let's take a look at the interface. That's this surface here, the interface between vacuum, which is on top, and the solid material at the bottom. There's a surface normal, and as long as you have normal incidence, the light enters from the top to this interface. There it doesn't really matter in which direction the electric field of the light wave is oriented. Basically, if light is approaching from the top downwards, the electric field of the light wave is in the plane of the interface here, is always perpendicular to the propagation direction. And so in this case, it doesn't really matter if the light has an electric field in this direction or in this direction. This changes if the light is not incident directly from the top, but at a certain angle. In this case, the light comes from here, a little oblique, and now it makes a difference for the reflection, for the amount of reflected light, if the electric field is oriented in this direction or in this direction. And we can see that in these two sketches. If we take a look at electric fields which are perpendicular to this plane of incidence, where the incident wave is, the surface normal, and the reflected wave, they span up a plane, the plane of incidence. And if the electric field is perpendicular, we call this S polarization. The S stands for a German word called senkrecht, that means perpendicular, and so S polarized means the electric field is perpendicular to the plane of incidence here. In this case, you can compute the amount of reflected light and also the amount of transmitted light into the material by equations called Fresnel equations. Pretty much straightforward. It just depends on the difference of the refractive index values above and below the interface. So these Fresnel equations are given, and there are two equations, one for S polarized case and the other one for P polarized radiation. And in the case of P polarization, the electric field of the incident wave is parallel to this plane of incidence. So it lies within this plane. So when the wave arrives here at the interface, the amount of reflected light and transmitted light is different compared to the case of S polarization, because there are two different conditions for basically the continuity of the electric fields, perpendicular and in the plane of incidence. Good. Let's take a closer look at the directions of the reflected and transmitted waves. And here, let me prepare this. I have prepared a sketch where light enters from a top vacuum, from a top material which has a refractive index 1. Only a real part, the imaginary part, is 0 for simplicity in this case, and the bottom half space here is filled with a second medium, which has a refractive index of which may be different. I can tune the refractive index values here. So let's take a look at the interface between air, refractive index real part is 1, and glass refractive index in real part is 1.5, or roughly 1.5. So here I can tune the angle of incidence. If we have normal incidence, well, everything is here in this one direction. There's a light wave coming here, reflected, going back to where it came from, and the transmitted wave goes just straight downwards if I'm exactly at 0 degrees. If I go to larger degrees, let's take a look at 8 degrees, because this is an angle which is realized in most spectrometer systems. Then you have basically an angle of 8 degrees between the surface normal and the incident wave here. What we find is the angle of the reflected wave here is also 8 degrees between the surface normal, but of course the reflected light is on the other side of this plane here. The transmitted beam does not show up at 8 degrees with respect to the surface normal, but it's a smaller angle. And basically this is given by the law of refraction, which relates the angle in medium 2 to the angle in medium 1 and the refractive index channels. That's drawn here. If we go to larger angles, this deviation, let's go to 45 degrees. The deviation between the angle here in medium 2 and the angles in medium 1 gets much bigger. Still, there's only one reflected direction. That's very important. So there's one incident beam, there is one reflected beam, and one transmitted beam. There is no scattering to the side as long as you have a perfect interface with no surface roughness and other problems at the surface. So there's only one direction where you can pick up or measure reflected radiation, and there's only one direction where you could measure the transmitted intensity, well, if it would be possible to place a detector inside this medium 2. Usually you have to go out on the other side through a second interface or through a sequence of more interfaces until you are back in vacuum or air in order to measure something with a detector. Good. So these angles, they depend very much, the angle of the transmitted beam depends very much on the refractive index of medium 2. If we make that larger, like in tin oxide, silicon nitride, or titanium dioxide or diamond, then the angle here gets smaller. In high refractive index materials like silicon, it's only 12 degrees, although we are incident at 45 degrees or 46 degrees in this example. So the radiation is very much concentrated to very small angles here. Actually, if we change the angle of incidence from 0 to 90 degrees, we go to very oblique angles. You can see that the transmitted beam inside medium 2 is only at 17 degrees. So all the radiation that penetrates into medium 2 here, imagine that this would be a silicon wafer, is concentrated between 0 and 17 degrees. So it's just a small cone of radiation that we have here. There is no radiation never going in this direction. And okay, this can also be reversed. If you start here with a high refractive index where the light comes from and you end up in vacuum, So we start in silicon and we end up in vacuum. Then basically for a large area of angles of incidence here, there is no transmitted beam at all. There is no light. Only if we approach at a small angle, there is a light wave that can emerge from medium 1 into medium 2. So only if we have small angles, there is light escaping silicon. If we cross a certain threshold, and that's called the angle of total reflection, what happens is that there is no transmitted beam at all, no radiation in medium 2 at all, and 100% of the radiation is staying in medium 1. So we have a straight 100% reflectance in this case. That's called total internal reflectance. And this is widely used in optical fibers, where you have basically typically a glass interface, and outside in medium 2 there's a smaller refractive index. And in this case, if you go to large angles, light moving at large angles through an optical fiber and it hits an interface, the reflectance is 100%. And this way you can transmit radiation over many reflectance without any loss, many kilometers, hundreds of kilometers. The only loss is due to absorption on the long path through these fiber materials, which must be obviously very clean in order to avoid absorption if you really want to go long distances. Okay, now we have learned almost everything that we should know about reflection at single interfaces. So let's now go to a case where we have two interfaces, and let's do it first in the regime of large geometric dimensions. That means geometric dimensions which are much larger than the light wavelength. In that case, we can ignore the wave propagation of light. That's a very good approximation if all the geometric dimensions are, let's say, 10 or 100 times larger than the wavelength. Let's take a look at the light propagation through thick plates, where we have two interfaces, medium 1 here, an interface to medium 2, an interface to medium 3. So a thick plate of a material, for example, where we have vacuum here and vacuum there. The situation then looks like this. You have an incident wave or light beam from here. As I said, we can actually, in this case, ignore the wave nature of light. We just can imagine this is a kind of beam, a pencil of radiation with a certain intensity. And at the first interface, we know already what happens here. We have seen that some minutes ago. Part of the radiation is reflected. That is governed by the so-called Fresnel equations. Part of the radiation is transmitted into the second medium. On the way here, in the second medium, there is absorption, governed by the imaginary part of the refractive index. The speed of light doesn't really matter too much, but the intensity is diminished by the absorption in medium 2. Then this second beam here, the transmitted beam, hits the bottom interface. Part of it is reflected, part of it is transmitted, and is emerging on the bottom side here. The partially reflected beam here goes up, shows up again at the top interface, is partially transmitted, partially reflected, and goes back. So once this beam here hits the second interface again one part of this is reflected, and so on. So there's a sequence of transmitted beams, there's a sequence of reflected beams. So this is called multiple reflection, And the only thing we have to do now in order to compute how much light is reflected is to add up the intensity of all the reflected partial beams. And if we want to compute how much light is transmitted, we have to add up all the intensities of those beams here, which is very simple. Let's take a look at an example, a light beam passing through a glass plate. In this case, I can tune here the glass thickness in millimeters. Let's start with a 1 millimeter float glass. We have discussed the optical properties of float glass in the one of the previous tutorials already. This was dominated by an interband transition somewhere here in the ultraviolet far away, causing an almost flat real part of the refractive index. There are some vibrational modes here, and as I mentioned in the previous tutorial, the absorption here is not zero. It looks like it's zero, but there are small, weak absorption bands, and we will now see how they work if we go to thicker and thicker glass. What you see here in the bottom curve is the reflected intensity, the intensity reflection, sorry. That's this solid curve. The dashed curve is the transmission. And what you see here, transmission is almost zero in the ultraviolet. There was some absorbing interband transition. In the visible, the transmission is 90% or higher. And then in the near infrared, it's still 90%, but then it drops down significantly quick. And in the mid infrared, where we have these vibrational modes, the transmission is zero, and the reflectance is about, on the average, maybe 20% or 15%. And there are clear structures related to the vibrational modes, clear reflectance features, which are characteristic for glass. So let's now go to larger thickness values. Let's go to 10 millimeter glass. And what you see now is that the near infrared regime is affected. The transmission is not 90% anymore. It goes down. It goes dramatically down here, around 1000 nanometers wavelengths. And this broad dip here, these are impurities in glass. These are ions in glass which absorb near infrared radiation. And if we go to 20 millimeter glass, you will see that this takes away almost 1/2 of the radiation already. The transmission in the visible is also affected. It's not 90% anymore, but between 80 and 90% for thick glass. And in particular in the red here, we have a quite strong absorption. And if we go to thicker and thicker glass, I increase the thickness of the glass, you can see that the transmission in the red goes down. And if I increase and increase, actually only green and blue light is surviving. Here is the visualization of the color, so of the transmission color. So what you see here is that the red light, due to the ion absorption, is decreased a lot. The amount of red light, the green light survives best. So thick glass light that has traveled through thick pieces of glass has a greenish appearance. Looks greenish blue, and this is what you can observe in any glass factory. If you have large piles of glass, it all looks green. Okay, let's take another look at light propagation through a thick piece of material. with two interfaces. Let's take a look at light propagation through water. And I do this for a special reason, as you will see in a moment. I have shown here the absorption, or the optical constants of water, with 1.33 in the visible, almost constant, and small absorption bands in the infrared. So there is water absorption, strong absorption in the visible, a little bit absorption in strong absorption in the infrared, a little bit absorption in the visible. And if we go to large thicknesses, this is 500 millimeters. Let's take 1,000 millimeters, 1 meter of water. You can see that the transmission in the infrared is almost zero. And the transmission here shows up at the edge between the visible and the near infrared, where the red light starts that we can see with our eyes. It goes up to very high values, and in the ultraviolet it drops down again. Actually, these optical constants here are for very pure water, distilled water. If we would take a look at water that you will find in a lake or in the sea or in an ocean, there would be more absorption in the ultraviolet, significantly more, so this would be zero also here. Unfortunately, I don't have reliable data for seawater, normal seawater in the ultraviolet, so I have to do this simulation with very clean water. But what you see, actually, if you go to a little bit larger thicknesses, 1.5 meters or 2 meters, what you see here, the transmission basically reflects the sensitivity of the human eye. The transmission is high, where we can see light, and the transmission is zero, where our eyes cannot see light. And actually, this is a strong indication for the assumption that our eyes have been developed underwater when we were beings living in depths of 1 to 2 meters, very shallow water. If we would go to thick water layers, let's say 10 meters under the sea level, for example, then there is no red light reaching our lights anymore. It's only blue light and a little bit of green light that we see underwater. So if our eyes would have developed there, we would not be able to see red light at all. So probably our eyes have been developed when our predecessors have been living in water, but in shallow water. For us here on Earth, outside the water, it would be very practical if we could see near-infrared radiation, because we would judge the quality of food. We could see how hot a body would be, but unfortunately we can't. And this problem of our eyes is due to the fact that the eyes developed underwater with no reason to have sensitivity for near-infrared radiation, because there is never light in the near-infrared in a 1 or 2 meter water depth. Okay, this was a little excursion in biology. Let's take a quick look, only a very rough look, at many interfaces which are all apart from each other by large dimensions, a few microns at least, or many microns, much larger than typical light wavelengths. In this case, you can treat all the interfaces separately, one after the other, and have intensity traveling between the interfaces. This is a regime of ray optics. Here I sketch basically the light propagation through a piece of paper, where we have this situation that if you enter a light beam into paper, You have scattering events at many interfaces between wooden fibers or titanium dioxide fillers or some other filling materials or voids in paper. And typically all the dimensions are in the range of a few microns. So you can treat every interface as if it would be a single interface, and you can compute intensity, reflection, and transmission. Then follow the light traveling further on to the next interface. Consider the absorption while it travels through a homogeneous material, and then when it reaches the next interface, you treat the next interface as if it would be separate from all the others with its reflection and transmission coefficients. If you do that many times, you can follow a light ray traveling through this scattering material, and you can record where it comes out and which direction it will then have. And if you do that many thousand times with a ray tracing software, you can predict where all the radiation is going, where how much light is absorbed, and where the light is going in far distances. So you can really follow and record the intensity of light everywhere in space, as long as all the dimensions are much larger than the light wavelengths. This is called ray tracing, or incoherent superposition of light waves, where we just add intensities. There are some problems that you can solve by ray optics or by this ray tracing. For example, if you have light propagation, light incident from the left through a drop of water, you can record the intensity of light everywhere, and this is a very good approximation for what happens in a rainbow. So if you add the intensities up for different observation angles outside this water drop, you will find a large intensity in the forward direction, and in the directions to the side. You will find two peaks, and basically you can predict that for blue light, the peak has a different position at a different angle than for red light. So there is a separation of color by water drops, which causes the rainbow, the colorful rainbow. This is the first reflection. The second reflection, the second internal reflection, causes a reverse direction of these colors that will show up when you observe them. That's the second rainbow. There's a bright dark zone in between, the dark zone between the first and second rainbow, and this is all well known from observations that you can do yourself. And the simulation based on ray tracing here, completely ignoring the absolute size of the water drop, is a very good approximation, at least for large water spheres. Okay, this was enough for ray optics. Let's now go to the topic thin film optics. In the case of thin film optics, things get a little bit more complicated with some surprising effects that are due to the wave propagation and that are due to coherent wave propagation that we have to take into account if the interfaces or the distance between two interfaces is in the order of the light wavelengths or even smaller. Let's take a look what can happen if we have a wave in a single thin film. So here we have, just in this example, we have vacuum, a material with a certain thickness. I can tune the thickness here from 0 to 1000 nanometers, and vacuum on the other side. This is obviously mechanically very unstable, and I'm not really seriously discussing this as a real example. I just want to use this example to show you an effect that is due to the coherent superposition of waves in a system like this. So what you see here, let's make an example. What you see here is a wave incident from the left, and you can see that that's no surprise, a reflected wave. There's a wave traveling through the material from the left to the right. It's partially reflected here. You can easily see that. There's also a wave traveling from the right to the left in this material. And on the right side here, on the escape side, the transmittance side, let's say, there is a wave that moves to the right and never comes back, because in our simple model there is no further interface to the right. What I show you here is the intensity transmittance as a value, in this case 7%, and on the reflectance side, the intensity reflectance of 9% in this example. So let's now try to consider some cases. Again, let's handle metals first. That's pretty easy. Actually, if you have a metallic system, 2 is about the same as N is about the same as K. What you see here is that even for very thin metal layers, the transmission is 0. The reflectance is what you get from the first interface. We have discussed that in the previous section already. So for thin metallic layers, there is no big surprise. Noble metals have a high reflectance, 0 transmittance, even for very thin layers. There is no transmission. You have to go to very thin layers in order to see radiation going through, but it's very, very dark on the other side. Okay, let's take a look at the dielectric material, K equals 0. And let's take a variation of the refractive index starting at 1. Of course, if it's 1, the material looks like vacuum. The reflectance is 0. The transmittance is 100%. Basically, for the light wave, this is not a layer at all. It's a piece of something like vacuum in between 2 half spaces of vacuum, and there is nothing that is happening here. If we go to larger refractive index values, of course, now there is a reflectance and transmittance. And let's see if I can generate a situation like this. Okay. Now we have a refractive index of 1.6. We have a reflectance of 0 and a transmission of 100. So now, even if the light wave has to travel through a material of a rather high refractive index, there is no reflection at all, and there is 100% transmission. And this is very surprising, because we know from our consideration of a single interface that with this refractive index, you have an intensity reflection of about 4 to 5%, actually I think 5% on the first interface. So if we would make this layer thicker, and we introduce a little bit of absorption, we switch off the backside reflection, basically we can do that. So in that case, you see we would have 7% intensity reflection from the first interface. So now nothing comes back from the second interface, and we have 7% reflection. If we make the layer completely transparent and we generate, I hope I can find the right thickness again that I had before, something like this. We generate a reflected wave from the second interface that adds up to the wave which is reflected here directly. Then they can superimpose to a zero amplitude on this side. So actually we have a wave reflected from the first interface. We have a second wave that comes from the second interface and is transmitted here at this first interface into the left half space. And if they have basically the same amplitude but opposite sign, one with a plus sign, the other one with a minus sign, then they can add up to zero, which is only possible if we use coherent superposition. That means superposition adding up with the right phase of the waves. So in this case, in the case of thin films, it is very, very hard to predict by just knowing the numbers here intuitively what happens. What you need to have is a simulation applying all the formula like Fresnel formula and the absorption within materials to really compute how much light is reflected and transmitted. We will do some exercises now. We will consider some effects of this coherent superposition of partial waves in thin film systems. Let's take a first example. Let's find an anti-reflective layer on glass. This is needed for optical components where you have the transition from vacuum or air to glass, which leads to a reflectance of 4%. We have seen that previously, and if these 4% are disturbing you, let's say in lenses for photographic objectives, then or for all kinds of projectors, if you want to avoid the few percent of light at an interface, you have to add a so-called anti-reflective layer. And so you have to find a thin film that just uses this coherent superposition to bring down the 4% to zero. Let's see if we can find that. If we have a single layer on glass, an anti-reflection coating with a certain refractive index, and we have to find the right combination of thickness and refractive index in order to make this reflectance zero. Right now it's 13%. Actually, this is not our goal. So if we would go to lower refractive index values as the one of glass, we will have some chance to reduce the reflectance. We now have only 2%, so we are on the right track, but I have to find the right thickness also. So this is now only 0.5% with a thickness of 100 nanometers. Maybe I can tune the refractive index value a little bit to get larger values, to get smaller values. So now this is below, this is 6 to the minus 4, which is almost zero. So this would be an almost perfect anti-reflective layer. Tuning the thickness a little bit. Well, I will not really try to get a value closer to zero now. But you can see that it works if we find the right refractive index and thickness for this layer. Well, unfortunately, this was only one wavelength, so there is a drawback of this single layer. If you have the goal to reduce the reflectance for many wavelengths for the whole visible, this will not really work. I will just show you the best that you can have with a traditional magnesium fluoride layer. If you take about 100 nanometers of this material, which has a refractive index below 1.4, but it's still too high for perfect anti-reflection. If you use that, magnesium fluoride has been used for a long time as anti-reflection layer. The anti-reflection can be large, about 3% reduction of the reflectance for the green, but not for the blue and the red. So there is it's not completely nice here. In order to do that more efficiently, you have to invest in more layers. And so if you use 3 or 4 layers, you have a higher chance to get close to 0 for all wavelengths. I will not discuss this case. Let's take a general discussion of a dielectric layer on glass. And what I will show you here is from 300 to 1000 nanometers covering the visible range. I will show you the transmission in blue, the reflectance in black, and the absorption of the total system in white, the dashed white line. And I can tune the thickness of this prototype dielectric layer, and I can tune the refractive index value here. And I would like to discuss a few effects. Assuming that we have a constant refractive index, if you have followed the tutorial about optical constants, you know already this is not realistic. We have dispersion, and we also have strong dispersion in the ultraviolet in most cases. But to make it simple here, I will discuss this case with a constant refractive index, knowing that this is a strong approximation. Let's start with a value, since we are on glass, of glass itself, 1.5 roughly. If we have a refractive index of a material of 1.5 on glass, which also has a refractive index of roughly 1.5, then it really doesn't matter how thick the layer is. If you start at 0, you get a certain reflectance and transmittance. If you increase the thickness, you're depositing glass on glass, and the spectra will not really change. This changes if we deposit materials of a larger refractive index. Let's take a value of 2 for silicon nitride or tin oxide. Then what you will see here, depending on the thickness of the layer, you see regular structures here, maxima and minima. The maxima are due to constructive interference between partial waves reflected at the top interface here and the bottom interface. And the minima are caused by destructive interference. You can see the minima, basically they are at the level, the minima in reflectance, they are at the level of the glass itself. So if we bring down the layer to 0, that means there is no layer. We have a level here of 8%. And increasing the thickness of the dielectric layer leads to these so-called interference patterns where the minima are still at 8%. That's the glass level, and the maxima here are higher. If we increase the refractive index, let's go to titanium dioxide, then the maxima rise, but the minima still stay at 8%. This is still the glass level. So the maxima, basically the position, the height of the maxima, tell you something about the refractive index of the dielectric layer, and the minimum here doesn't tell you anything about the dielectric layer, just about the substrate. The position here of the maxima, they depend strongly on the thickness, so you can move them to the left and to the right with the thickness, and you can move them up and down with the refractive index of the dielectric layer. So once you observe a maximum here, you can tell from its height how high the refractive index should be, and from the position concerning the wavelengths, you can tell something about the thickness of the layer. If you go to very thin layers, let's say between 0 and the first maximum, then you see basically just one very broad maximum, a very broad minimum in transmission, and this can be rather colorful. You can here I have a visualization of the color in transmittance and the color in reflectance. Here there are the detailed values, the color values. So single thin films on glass can have very colorful appearance depending on the position of the maxima and minima in transmission and reflection. Here we have the second maximum, and that we can shift to the blue in reflectance, to the green, or to the red, and depending on the actual position, you can have very colorful appearance of dielectric layers on glass. And that's a side remark, the color also strongly depends on the viewing angle or on the angle of incidence of the radiation, and that can also lead to very colorful appearance of coatings on substrates, thin film coatings on substrates. Let's take a double layer on glass, and here I will discuss a double layer made of titanium dioxide and SiO2, and what I can tune here, actually I can have a sequence of double layers. The high refractive index layer is called H, that's the titanium dioxide. The low refractive index layer is called L, that's SiO2. And what I can show you here in this simulation is a so-called Bragg reflector, where you have a certain number of double layers. I can tune the number of double layers here from actually 1 to 20, I think, or 15. And depending on the number of double layers, you can see a very high reflectance, which is called a Bragg reflector. I can also tune the thickness of the titanium dioxide layer and the SiO2 layer. And what you see here in addition is the color in reflectance and the color and the transmitted radiation. Let's take a high number of double layers, like let's say 15. That means 30 layers have been deposited. And with the thickness values of the layers, I can shift basically the high reflectance that you get here, and this is very close to 100%. I can shift that to any wanted color or to any wanted wavelength, and so I can make a reflector for the blue light. And with the thickness, I can tune the width. I can shift it to the green light, to the red. And these so-called Bragg reflectors are used for high power laser mirrors because the absorption in this stack is almost zero, very close to zero, because the coherent superposition of partial waves avoid that light reaches the glass, so all the light in this maximum is reflected within the first maybe 10 or 12 double layers, and if these materials are almost absorption free, usually deposited by evaporation, very slow evaporation, then you can achieve absorption values which are very, very small, and to make mirrors for high power applications. Okay, let's take a look at some other layers on glass. First, let's take a look at a silver layer, where I just show you what happens for different silver thicknesses. If we start at 0, we have the glass properties. A few nanometers already are sufficient to increase the reflectance significantly, at least in the red, and to decrease the transmission. if we go to 10 or 20 nanometers, the reflectance in the visible is already much higher than 50%. In the infrared, it's highest. And if we go to large silver thickness, like 60 or 100 nanometers, you can see that the reflectivity in the visible is above 90%. Not really very much above 90% for blue light, but at least for red light. And values here, like 100 nanometers, they are typical for silver mirrors that you use in your bathroom, and you can live with this little problem here of the lower reflectance in the blue in those applications. Okay, a gold layer looks a little different. Even if we make a gold layer very thick, like the silver layer, 100 nanometers, the reflectivity is high in the infrared, but in the near infrared, but not in the blue. You can never reach a high reflectance in the blue with gold, just because there's not enough charge carrier excitation. In this case, I have discussed that in one of the previous tutorials already. A chromium layer is shown here as a typical example of a highly absorbing layer, a highly absorbing normal metal layer. Chromium has refractive index values which are not very high, and N and K are almost the same, I think in the range between 1 and 4. And here you should take a look at the absorption. The absorption rises very, very rapidly if you only deposit a few nanometers of chromium. If you have 4 nanometers or 5, let's take this example, the absorption is 30%. It's almost evenly distributed in the visible. So for all wavelengths, also the near infrared, you find strong absorption of 30% by a 5 nanometer layer. The absorption is not rising too much. If you increase the thickness, it's even going lower because less and less light comes back from the bottom interface. So if you deposit a thick layer, you basically see the reflectance of the top interface. There is no light going through the chromium layer that would increase the reflectance. And so this is actually an example for a thin metallic layer that can be used as a very efficient absorber. And if you use several of these layers in a layer stack, you can absorb almost 100% of the radiation within a coating. Sometimes this strong absorption is not wanted, like in a I will discuss in another tutorial the properties of glass coatings, where nickel chromium layers or titanium layers are sometimes used as so-called blocker layers, and if they would not be oxidized, they would absorb a huge amount of radiation, which would destroy the positive properties of those coatings. So in that case, you have to carefully make sure that all the normal metal layers in the stack, like nickel chromium, are completely oxidized. So you turn them into a transparent, absorption-free oxide. Let's discuss at the end a TCO layer on glass, where you have basically a single TCO on glass, which can be tuned to a certain color, if you like. Actually, the thickness that you need for a certain application, like using the TCO in a display or in a solar cell, the required thickness depends on the doping and on the conductivity that you need, or on the sheet resistance that you want to have. So if you need a certain conductivity, you have to produce the TCO in a certain thickness. And as you see here, depending on the thickness, there are the shifting maxima and minima of the interference pattern. We have seen that on the dielectric layer on glass example, and this has to be carefully chosen in any application. If you have thick layers, you have many of those fringes, and they take influence on the color of the complete coating. In the touch display, for example, you have more coatings than this, or in an electrochromic window, you have several layers, in particular 2 of the TCO layers, and in this case, the coherent superposition of waves in thin film systems is very important to be taken into account for the design of the total product. Okay, this was the last example that I would like to show you in the general discussion of light propagation in thin films. There will be more tutorials discussing technical applications of thin films, in particular one about glass coatings, which are important for buildings and cars. But thanks a lot for your patience today. Bye-bye.